Mr. Yashwant, am I audible?
Yes, sir.
Yeah, we can start. Just let me to do the formalities.
Yeah, sure,
Yeah.
sure.
Good afternoon to all. On behalf of the organizing committee, I, Dr. Malay Kumar Nath, the coordinator, and Dr. Sanjay Bankapur, the co-coordinator of the FDP, welcome you all to the third day, session 3 of the online Atal FDP on harnessing AI for medical signal and image diagnosis. It's my pleasure to welcome Mr. Yaswant, Senior ASCII Digital Design Engineer in Synopsys, Bangalore. Mr. Yaswant will deliver the talk on VLSI implementation of Hopfill neural network using stochastic computing for skin cancer classification. Please join me in welcoming Mr. Yaswant to lead today's session. Over to you, Mr. Yaswant.
Thank you, sir. Thanks for warm welcome.
Yeah, thank you.
Yeah, I'll share my screen. Let me acknowledge someone.
Yes, please share. Yeah.
Is my screen visible? Sir, is my screen visible, sir?
Yes, Mr. Yaswant, it's visible.
Yeah. Thank you. I think it's good to have the continuation after the Naveen session because most of basic introduction details, I think Naveen is covered. So now we can see the extension of his work with the other neural networks, not with the CNN. He has done with CNN. So we are going to execute this same classification using the Hopfill neural network. We will see whether it's a compatible or not compatible for the skin cancer disease classification. So today we're gonna discuss about VLSI implementation of Hopfill neural network using stochastic computing for skin cancer detection, skin cancer classification. So I'm Ashwant and I'm working as a senior ASIC digital design engineer in a Synopsys. So we will see the objectives of what we are going to see here. Implementation of Hopfill neural network to classify the skin cancer detection using the Python, and then we will try to implement that on FPGA. So all this introduction I think he has covered, so I will go little faster here. So it's a most common cancer. Then we are going to see the uh, classification on melanoma or non-melanoma. So if you see melanoma is a deadly cancer compared to non-melanoma. So if we are able to detect it at pre-mature stage itself, we can avoid the death rate. So all these are statistics of that. Then literature survey on that, how we are going to do. Then we are going to see design methods of skin cancer and identify the nature of a skin lesion by leveraging the deep learning approach. So we will see. We are investigating this on SIAM ISIC 2020 dataset. So this is the classification of groups, how skin cancer is classified. You may see the previous slides like SCC, BCC, MEL, AK, NV, BKL, and unknown in the skin cancer detection data types. So we are going to see a little bit about the data set, how it is organized and the frequency of the each data. So if you see here, there are more data of unknown compared to all the diseases. So if you are giving this, the model might overfit in the sense, whatever the data you give, it will tell unknown because of the frequency is different on each sample size. So what we are going to do is we will do little pre-processing and give us an input to the network so that it will be equally distributed. Then we will see the gender bias, how it is between the male and female. If you see properly, it's like almost same on both male and female. Then location of this cancer on the different parts of our body, then different ages. So if we observe, it's a mid age. We see more. It's more accurate on the mid age compared to the lower mid age. So proposed methodology is that we are going to take a data set of different data sets and pre-process this. Pre-process consists of a blur, distortion, and resize. Then if you see, there is a one more block of a classification, segmentation, pixelation, and normalization. So the input that we are taking from the data sets, we are not going to give it as it is. So we are going to do some pre-process. So these are the different pre-process techniques that we are going to use. So after end of this, we are making as a training data set of 80% and validation as a 20%. So we are going to give it this to image generator and validation data set to deep neural network to check whether this network is processed correct or not. So this is an interface engine where the class labels we are giving to the data sets that we are trying and testing. So here we are going to see what is meant by Hopfield neural network. So what is the use of Hopfield neural network? Why we are selecting this neural network? We have that question, right? So let's see. Actually, it's a recurrent neural network where the feedback is given to the input. So based on the feedback, previous output, this the weights will be changed. So that's why we call it as a feedback neural network. And also it is having only single layer of neurons. That is the advantage of this Hopfield neural network. Because of the single layer, it should be faster, and the implementation in a hardware it's comparatively very less. If you take with a CNN or HNN, sorry, CNN or ANN. So that's why we are taking as a Hopfield neural network. So here, if you see it's a discrete Hopfield neural network. If n is the number of neurons, then the weight matrix of this Hopfield neural network is n cross n. So if you observe this diagram, we see that each of the output neuron is connected to each other neurons. So whatever the output coming as y1, it is connected to the other outputs also, the other inputs also. So this is circuit topology, how it is created in DHNN, that is discrete Hopfield neural network. So how the weights will be changed in a Hopfield neural network. So it was introduced by Donald Hebb. So it's an unsupervised learning. So because once you give the feedback, automatically it won't depend on ours to give some input. That is what we call as unsupervised learning. So this is the weight expression that will change whenever there is an synchronously activated the synapse. Then the weight of the synapse will be increased. If you see, if yi and yj is synchronously activated, then it will be both are plus. If we take asynchronously activated, then it's like minus. One is plus, one is minus. So this equation will become t plus 1 equal to wt minus of a into yi and yj. So at that time, it is decreasing the weight of the uh, total next weight. So that's how we will be calculating this. So the results of this, when we give as an input of our data set, I said, right, we are doing pre-processing to make the balanced data set. So we are taking this set image as labels, as you see in the screen. Then we are making it into 200 samples of each image and making as an output balanced data set of each samples, so that at least HNN, the neural network will train equally. Okay. So after this, it will be recognizing the patterns like this. And this, if you see, it's a black and white only. Like a Hopfield neural network can classify only after the pixelation. After the pixelation. So initially what we will do, the colored image is sent to pixelation method. After that, this grayscale image will be detected as skin cancer now. So these are all the trained weights of the each neural network. So it's different for each size of the image. So we are taking the different sizes of the images to see which size of the image is compatible, or which size of the image is giving good accuracy and results. So here is the differences between the training time, training accuracy, and validation accuracy. we see the each even normal small feature sizes of 28 cross 28 is also taking us 4 hours 20 minutes training time, and training accuracy is 4.1, validation is 3.2. Like that, we are increasing the feature size, I mean image size we are increasing, and we are checking how much training time it will take, training accuracy and validation accuracy. And at the end of the result, we see the 120 cross 120 images are having good training accuracy and validation accuracy compared with other models. But that is, even though it has a training time of 6 hours 32 minutes using HNN. So these are the pictures that it reflected. So if we see the balance and threshold, or what this figures meant for, once after some time, I mean each sample it is classifying, and the threshold of the CPU is going high. After certain point it's decreasing and leveling it at some threshold voltage, that is 0.3 is the threshold voltage. So it's with different aspects of a image. So if we see, it can be used for digit classification, and it's a now we are seeing for skin cancer detection, right? So when we compare the training accuracy and validation accuracy, it is very less. If you see, training accuracy is very less, like 16.3, and validation accuracy is 15.1. So from this we can conclude Hopfield neural network is not efficient network for image classification, but it is good for pattern recognition and pattern restoration. Since a single layer network not robust for larger datasets, we can't use larger datasets. That's why we are taking only 200 samples. So second phase of this, we I think Naveen has covered this HLS model, how we are going to uh, module each of the neurons in hardware descriptive language. So I will not going through this. So I'm going to see how I implemented this in hardware. So each steps we are going to implement in hardware. So hardware used is FPGA. The board is this board, and software is used to dump this one is Vivado. Jupyter Notebook to train the model and give the weights to that model. Then Vivado HLX is the main tool that we used for VLSI implementation. So clock frequency, if you see 250 megahertz of the clock that we are going to use in this implementation. So I think everyone knows that what is perceptron and how perceptron will works, right? So I will give a little bit of a introduction for this. So it's a net input function and weights of the each inputs. So it will be like multiplication of each input that is giving to the function, and activation function will works as a filter between input and output. So this is the output equation, wi into xi plus b. This I am going to implement in a hardware. How we are going to implement in hardware? So the block diagram of a perceptron, each perceptron is like this. If you see the weights that we are going to put it in a RAM, then those weights are giving it to a multiplier, and the input is multiplying to that. So after the input is multiplied with the weight, that is giving to the adder, which is having the bias. So it will add the bias and combo logic of this weight memory and input, and give me the resultant output. So this will have the sum of the inputs and input and activation output. So if you see, this is what we are implementing there, wi into xi plus b. So wi into xi plus b bias. Then we are giving an activation function, and then output will be coming here. So we are considering two activation functions to implement in a hardware. So most of us thinks that linear activation function will take lesser hardware compared to the non-linear activation function, but it's we'll see what is exactly true. So we are going to take an example for the linear activation function or non-linear activation function also. So linear example we are taking as a ReLU as an example. So non-linear we are taking as a sigma. Then we might have the doubt that how we are going to implement in hardware, because it's a continuous signal, but in digital it's not possible to infuse the continuous signal. So what we will do, we will separate each signal into minimal time and split that way. So this will be converted into discrete, and these values are stored in a RAM that is giving it as an input to the function. So when we do this, this is the RTL architecture. Once we implement this in FPGA board, this is what the RTL architecture that will reflect. So here I will give the count and timing details. Uh, Here slack, in the sense, in general in VLSI, the slack is the main factor in any circuit design or any subsystem designs, because slack is the difference between actual desired signal time and the time of arrival of the signal. So that is what the delay. So here, in whenever we are designing any system, any circuit designs or digital designs, the main perspective is power and delay, then hardware. These should be minimal so that it will be effective. So here, if you see, the setup time is 3993.241 nanoseconds. We are converting that frequency into the nanoseconds, and the total endpoints is 154, whereas whole time is 0.185 and pulse width is 1.5 nanoseconds. So we are going to check the timing analysis. So Fmax, we know how to calculate 1 divided by 2 into T minus worst slack. Worst slack is the minimal time that required for a actual signal and desired signal to arrive. So when we calculate this, we see 249.57 is the Fmax that we can use in this. We can use in this RTL. So this is a critical clock path for the relay activation function. Then on-chip power calculation. This will be calculated by the tool. So total on-chip power will also should be small, because power is also a concern when we are designing any digital design. So here we see 0.104 watts is the on-chip power that it consuming. So if we see this properly, since we are implementing in a hardware that is FPGA, it already have the LUTs, flops, and DSPs to implement our functionality. So if we take this as an example, relay activation function. So if you see the resources, how it is utilized. See, LUTs, there are 74. This is total and utilization percentage 0.14, and flip flops 66 flip flops, 2 DSPs, IOs 36 input and outputs. Buffers that we are using is only 1. So that is the hardware utilization of the relay activation function. So relay sigmoid activation function, to implement this, it is little bit approach is little bit different. So what we are going to do here is, we can't implement directly in hardware. So implementing a predefined function values in a lookup table, and then this lookup table we are giving it as an input to the top design. So based on the data weight, we are having one script of a sigmoid function that will generate the LUT values. These LUT values we are storing in a RAM. That RAM is giving as an input to the top design, so that it will map the values of a sigmoid activation function. Okay, so this is the RTL with sigmoid activation function, RTL synthesis of a sigmoid activation function. So if you see, the worst slack is here 3993.882 nanoseconds, and hold 0.158 nanoseconds. Pulse width is 1.5 nanoseconds. So here we calculated the Fmax as 249.95, whereas here 249.57. It's almost equal for both Fmax. Then how we can conclude? That is the main thing, right? It is a critical part. And on-chip power of a sigmoid activation function is also same, 104 watts. So if you see the hardware utilization here, it is taking LUTs of a 55. flip-flops are 54, DSP is 2, IOs of same 36, input outputs, buffers is 1. So here, if we observe, it is taking less LUTs and flip-flops compared to linear activation function, ReLU function. So here, for comparison, the main three factors that we discuss already, that is power, delay, and area of implementation. So having same power utilization and maximum operating frequency, but sigmoid implemented in lesser hardware compared to the ReLU activation function. So this is the conclusion that we came after realizing in this hardware. So nonlinear activation function of a sigmoid is better compared to the ReLU activation function. Okay, this can be implemented. We had seen only one percept on how we can implement. This can be extended to a architecture of a 4-layer to classify the digits. Implementation of fully connected layer with a with hidden layers of 4, and this can be used for a classification of digits. This is the diagram for that. We can see 4 layers that we are going to use. Each layer, each perceptron is connected to each other, every other perceptron, and this output can be calculated. This output will be used. This output will be implemented in a hardware, and this will be used for processing. So that's it from my end. The publications that we did for a half-wheel neural network, and these are all the references. Thank you. If you have any doubts or questions, I can take it off. Hello, am I audible?
Yes, you are audible. Participants, if you have any queries, you can unmute yourself and you can raise a question to Mr. Yashwant.
Sir, good evening, sir.
Yeah.
Sir, other than FPGA, what are the hardwares we can use to implement, sir, for
Yeah.
classification?
In general, we can use the Raspberry Pi and Arduino to implement the hardware. But FPGA, why we are using is it's a similar to ASIC. ASIC, we know the difference, right? ASIC is a application specific. Only we can design and do for only one specific application. We can't replicate that for another device.
Yeah, Mr. Yashwant.
Yes, sir.
Yes, have you completed the things?
Yes, sir.
Yeah, okay. Participants, do you have any queries?
Yeah, I'm explaining
Yeah.
one doubt why we are going for FPGA.
Yeah, sure, sir. Yeah.
Yes. Actually, the FPGA is a similar to the ASIC. So ASIC, whatever we are going to implement before manufacturing, we are going to test in FPGA, because ASIC will be testing like production will be like a hell number of chips in general. So before going into the ASIC, we will be testing in FPGA. Okay, because already FPGA has the predefined LUTs and programmable units. It's a very easy to implement in hardware, and we are also checking with the real-time process, real-time inputs also. That's why we are going for FPGA, dumping in FPGA. We can check in Arduino or Raspberry Pi.
Thank you, sir. Sir, if I have written, I have compiled all the things in Jupyter Notebook, sir.
Yes.
So now how I can transfer it to that FPGA kit, sir? So
Okay.
now I am having a classification model. How I can implement it
First
in
thing
FPGA?
is we need to implement it in hardware level language. Whatever we had done is like software level, right? All these neurons, everything we are written in Python. But when we come into the hardware, it will reflects with the perceptron. So each perceptron code we are going to write it, and the connections of each perceptron we need to take care. Like if you take Jupyter Notebook, we have implemented like 14. Let's take an example of a 4 hidden layers, and then input layer, output layer. Now I had shown the example of only one perceptron, only one perceptron, how we can implement and which activation function we can consider. That's what, just one perceptron and one activation function which we can implement through hardware. That's what I explained now. So after this, we need to integrate this one perceptron to multiple perceptrons. Like we need to instantiate in multiple hidden layers, and we need to connect all these to uh, all outputs of a perceptron to input layer again. Then bias will change. So like that we need to do. Got it? We
Yes,
had
sir.
done
Thank you.
only software side, which will reflects like it will take our laptop hardware as an input and take the processing. So whereas it comes to the hardware, we need to write each and everything in a Verilog code. Each perceptron or each block, let's take a multiplier that we are multiplying the weight into bias, right? That weight into input, right? That will be taken by the 8-bit multiplier. That 8-bit multiplier code we need to write. Okay, so all this will be integrated in a single file, and this file we are instantiating in multiple times to replicate this same design in software.
Thank you, sir.
Yeah.
Hi, sir.
Hi, sir.
Am I audible, sir?
Yes, audible.
Sir, actually, I am not having that much awareness on implementing a neural network in FPGA, but I am having small clarification.
Yeah, sure.
To implement the off-field neural network for image segmentation.
Yes. Hello.
Okay. Yeah.
Yeah.
I'm asking, sir.
The
So,
thing
is it
is,
possible, sir?
no, because the main
Okay.
thing that we came to the Hoffel neural network to check on image classification is that since it's a single layer network, whether it will perform good or not, that's what we are testing initially. We know that CNN and DNN with the efficient with an efficient filters like efficient net or with those filters we can get good accuracy about 96 97 percentage also. But when we realize that in hardware it's like a number of perceptrons is very high, and it's a feedback network. So what will happen when the number of neurons is very high? We see that even a single perceptron is taking a large number of a hardware. Large number in the sense, let's take a 1% also. Each perceptron is taking 1%. Then I think we have n number of perceptrons in a CNN or DNN. So to avoid that, we came into the HNN, Hopfield neural network, where we have only single layer of networks. We don't need of multiple layers and multiple inputs. That's why we are testing within software whether it is feasible to classify the image or not. And the training time is also like a 6 hours, 7 hours. It's not feasible at the end. We concluded that it's not feasible at the for the image classification, but it is feasible for the pattern recognition.
Uh, yeah, understood, sir. Thank you.
Yeah.
Any questions from participant? I hope there is no more questions from the audiences. So I like to thank Mr. Yaswant for his wonderful session on Hopfield neural network. Thank you, Mr. Yaswant.
Thank you, sir.
I now request all the participants to on their camera so that we can have a group photo. Mr. Yaswant, can you stop sharing your slide? thank you all. So we have captured the photo. The next session will be taken by Dr. Norton Stephen. He will discuss about skin cancer, and the session will start at 6 p.m. So please join at 6 p.m. today.
Thank you, sir. Thanks for the opportunity.
Okay, sir.